Okay, hello everyone. Thank you for coming to this trustworthy a, data science and AI seminar. Today we are extremely happy and honored to have Professor Jian-Yun from University of Montreal to give us a talk. Professor there is with the Department of Computer Science and Operation Research, University of Montreal, and he is also the head of the Raleigh Lab on Applied Research on Computational Linguistics. Professor Ness' research is in the areas of information retrieval and natural language processing. He has worked on many information retrieval models, web search, cross-language information retrieval, recommendation systems, and deep learning models for query suggestion and dialogue. Professor Nair has published over 200 papers in the major journals and conferences in information retrieval and natural language processing. He is on the editorial board of 5 international journals, such as the Journal of Information Retrieval. He served as the chair, PC chair, or general chair of many major conferences in those areas. He received several Best Paper Awards, including a Best Paper Award and a Test of Time Honorable Mention Award from SIG-IR. Now, without further ado, let's welcome Professor Nair. Thank you. Yeah, please take the stage.
Yeah, thank you very much. I'm really honored to be invited to give this talk at this seminar. As I said before, I didn't know your seminar, otherwise I would have participated more often, and I promise you that I will participate more and listening to the other interesting talks in this seminar. And as Jian presented, I'm in the Raleigh Lab. So if you don't know the Raleigh Lab, I have the website here that you can check. Basically, the Raleigh Lab focuses on research about the computation linguistics and different applications, such as information retrieval, the NLP applications in industry, and also the question answering and so on. So there are many topics that are related to the research of our lab. So you can check out. So today I'm going to talk about one topic which I focus on very much currently, which is about the dialogue. But I want to push to the grounded dialogue. So we did some initial investigations on grounded dialogue to try to include some useful information in the dialogue instead of chit-chat. So that's the basic goal of our work. So let me just give this simple definition of what I mean by grounding. And this word has some meaning in the traditional definition of communication and the dialogue. So you can read like this. So grounding means that if you have a conversation with somebody, there should be some mutual understanding and mutual background so that you can drive your dialogue with the other party. So this is what means grounding. But currently in the research work, people are using this word to mean slightly different things. So by grounded dialogue, we mean that the dialogue should be based on some basic information or knowledge that can be found in a document or in a knowledge base. So this is what I mean by grounded dialogue in my talk. So for example, we can talk about the document grounded dialogue. In that case, we may refer to some information that we can find in the document in our discussion. And this is just one way to go to pick some additional information from the document and to integrate in our conversation. So this is about the concept of grounding of my talk. Now, dialogue is certainly familiar to you, and we do dialogue every day, and also computer dialogue is not new. So we have the famous ELIZA system that tries to drive a conversation with a patient, and this is the kind of a dialogue that we can imagine. And now we are more focused on data-driven approaches to try to generate some responses in the dialogue. So here, the goal is to mimic a human dialogue, and basically that's a kind of a chit-chat without a purpose in particular. And the goal is to produce some output given the input. And basically what we want to do is to use a large set of human dialogue data and try to use that data to train a model. And by training the model, we mean we want to train an encoder and a decoder so that when you have an input, you will encode the input somehow, and using the encoded information, you will generate the output by using the decoder. So that's the basic process. Now, the assumption behind this schema is that we have everything in the human dialogue data. That is, once you just use the human dialogue data to train your model, everything is there. So that's the basic assumption. And one typical approach to the encoder-decoder architecture is like this. So we have some input sentence, such as, "Mom, I don't feel so good." And this is a sentence that will be encoded somehow in the a representation. And then if you have the second sentence, that will be added in the representation. So along the way along the dialogue, you will have the representation that evolves. And at the end, when it is a stage to create some output, then this sentence will be generated depending on what you have in your representation about the dialogue. So that's the encoding and the decoding schema. Now, if we want to not only use the human dialogue data, but also some external resources, how can we do that? And typically, this is the current approach. Typically, we want to use a large text data to train a language model. And this is called the pre-training. That is, we have a large language model that we can use in a lot of NLP tasks, not only in dialogue, but also in machine translation and a lot of other NLP tasks. So here, the encoder-decoder still works in a similar way, but by relying not only on the dialogue data, but also on the pre-trained language model. So typically, we'll try to do a fine-tuning stage using the dialogue data to fine-tune the language model. So here, the assumption is slightly softened. That means we don't have everything in the dialogue data, but also we have to rely on the pre-trained language model. Okay. This trend of using pre-trained language model is really very hot in the current research area. So for example, there have been different dialogue model created using pre-trained language models such as the GPT, which is one of the large language model. So using this kind of a pre-trained model, it is possible to generate the responses for a human input. So here we have the user and then the bot, which is the system, will generate some answers, some reply, and the dialogue can go on like this. And you have this open source system that you can try on this website. Sorry. And also, there is even a Reddit forum where you can see that given some prompt, some topic, then the bot will generate alone the input and the answer. So here, the input and the answer are generated by the same bot, but you can observe how the bot can respond to its own input. That's funny, but you can try those systems. And this is just to show that the pre-trained language model is a current trend in this area. Now, in addition to the response generation approaches, what I just mentioned, there is also another family of approach which tries to use retrieval approaches to retrieve relevant responses from a large data set. And this data set is a large dialogue repository where you assume that you have a lot of rounds of human dialogue. And here the problem is to select some relevant, appropriate answer, appropriate response from that repository that correspond to the input. So it is basically a retrieval process. So, and this retrieved output could be adapted somehow to produce an output, but very often we don't use this adaptation. So basically we just use the retrieved output to produce, to present to the user. So this is a typical case, a typical schema used in the systems such as the shell ice. Okay? Now, given that the general approaches that we have, so we have the sequence-to-sequence generation of a response, we have the response retrieval systems. But what we can observe is that in all those approaches, very often we don't consider whether the response is grounded in something, whether we have a strong support or some information that will support the response that we will provide to the user. So here, I want to push in that direction to say, if I want to identify a response or generate a response, I want to rely on some knowledge or on some information that I can find in a document. So this is the purpose of my talk. Now, is it necessary to have dialogue grounded in something? Of course, very often when we just have a free discussion, conversation, not necessarily, we can use what we know already, what we have digested, what we have encoded in our mind to just drive the conversation. So this is what we do very often. But very often, if we want to discuss about some very detailed stuff, we may not recall those details. And we may want to check in some external resources. For example, if I ask you when we will open Canadian borders, and you don't necessarily know that. So you want to check in some document, and it happens, for example, that a news article talks about that. So you want to check in that document, and you can say, well, the document says it's August the 9th for Americans. So that's a conversation grounded in the document. And in the same way, when you ask the information about the capital of Armenia, you may not know that, you don't have that in your mind. And you want to check in some knowledge base, and then you can find the answer. This is the capital of Armenia. So those are two examples where you will need to check in the document or in knowledge base to construct your response. And grounded dialogue try to mimic this process to rely on some external resources to construct your response. So here I have this schema showing, I'm sorry, I should go here. So the goal of a grounded dialogue is to say, I have an input X, I want to produce an output Y, but also I have some external resource K here, and I want my output to be conditioned not only on the input, but also on the outside, on the external resource. So that's the purpose of grounding. Here I have two schemas One is the response generation schema. That is, you have your traditional training process to train the encoder decoder, but also you will try to mix up with the external resource in the encoding and the decoding process so that the output will depend on the external resource. And in the same way, when you use the retrieval-based response selection, again, the external resource will help to identify the most relevant response here to help the retrieval process. So this is the purpose of external resource. Of course, when you try to integrate some external resource into the decoder encoder process or the retrieval process, you have to figure out how to integrate that into the response. But also, I want to focus on this second problem, the selection of relevant information or relevant knowledge will be a key to make a good use of external resource, because you have very often quite a large external resource and only a small part is relevant to the current dialogue situation. So the selection, the appropriate selection of those parts of external resources is the key to help the response selection or generation. So that's what I'm going to focus on. Now, how external resources have been used in a few previous work. So I just mentioned a few previous work to show how people tried to deal with those problems. So this work, RefNet, is a document grounded dialogue. So we have here the generation-based response dialogue responses generation. So basically, what this system tries to do is to use the background knowledge, background document, to tell the system there could be some additional words that you can select. In addition to selecting from the decoder, you can also select from the document. So there is a kind of a gating that tries to tell the system whether the word, the next word in the response, should be generated from the model or should be copied from the document. So this is one way to use the external document to try to produce some more alternatives to the selection of tokens. So that's one approach. And this, well, the way to do that is here. So you can basically look at this element here. So depending on some probability, the system will decide to generate the token or to refer to some entities that you already have in the document, in the background knowledge or background document. So that's the decision relying on the background knowledge. And the second approach that I mentioned here is also a generation of response relying on external knowledge. But here, the external knowledge, which is also a document or a set of documents, is used to determine what's the transition from one topic to another. So suppose that you are discussing about something in your current dialogue situation. There are keywords, there are topics. So a set of keywords will refer to some topic. And you want to determine what will be the next topic that I should mention in my response. So this is viewed as a transition from some topic to another. So here we have the matching of your current situation, that the current input X with what you have in your background knowledge or background document. So you will have different degree of matching. And from that, the system will learn the transition by using different sizes of a window. That is, when I talk about this topic in a sentence, what I'm going to talk about in the next sentence and so on, and within 5 sentences. So those are the transitions that are observed in the document. And from that, we will determine what will be the transition vector, the topic transition vector that I can extract from the document. And that will be used to condition the generation of the response. Okay, so that's the second work. And then I'm going to focus more on the retrieval-based response selection. That is, we have a large repository of dialogue data, and we want to select the most relevant response from that data. And in this family, we also have different approaches trying to incorporate the document as a background, trying to select the response based on not only on the retrieval system, but also on the document. So here we have the first one that will model the document sentences as a memory network. That is, you store different sentences in a memory, and the dialogue context, that is the current utterance, together with the history, will be used to read the memory, to retrieve or to fetch out some relevant part from the memory. And that will be used to condition on the selection of the candidate response. Okay, so this is one typical approach. And the second approach is to consider not only the utterances in my current context, but also the document, different sentences in the document. And we will have a different comparison, different matching between the response and the current context, but also between the response and the document. And we have different matching signals that will be collected here. And at the end, the selection of the response will not only be based on the response and context similarity, but also on the similarity between the response and the document. So this is another typical approach. And the third typical approach is very similar. That is, when we consider the document, we try to construct some representation about the response, the candidate response, which is conditioned somehow about the context and about the document. So we will have two new representation about the response candidate, considering the document and considering the context. And then we will have different steps of matching to produce the final score. So here you can see some ways to use the document as the grounding element. Now, what we can observe here is that, well, typically when we rely on a document, that document can be very long. And the document can talk about a lot of different things. And when we want to refer to something in the document, usually we would just want to refer to a small part of the document. So this is to say that only a small part of the content of a document is relevant to my current dialogue situation. So the selection of relevant content is really important. Otherwise, you will bring a lot of noise, and that will not help in the response selection. But in the previous studies, the selection is typically based on the attention mechanism, which will try to weigh different sentences in the document. And you can imagine that you have quite a strong weight to the most relevant part, but you can also see a lot of small weights spread out on other irrelevant parts. And you can say, well, I have small weights on those irrelevant parts, so this is not so important. But if you accumulate a lot of irrelevant parts, the accumulated weight of these irrelevant parts will be very important. So at the end, you will return a lot of noise. So this is what is not well done in the previous work. So what we try to do is to process a hard selection instead of selecting just weighting the different sentences, we will just select a small number of sentences. And the second problem is that in the previous studies, we typically just consider the whole history and the current utterance as a whole. So we don't have necessarily a weighting about their importance. But in practice, when we drive a conversation, the most recent utterances are obviously more important than some distant utterances. And this fact is not considered in the previous approaches. So what we do here is to just use a decay function to assign more importance to the recent one. So I'm going to present the work to incorporate those two elements. Let me just tell you a little bit about the context of this work. The context is to have a conversation about the movies. So we have a description of movies. So here we have a description about this movie, about who played in the movie, what's the genre of the movie, and a short description. Okay, and we have a context of dialogue. So you have different turns, the U1, utterance 1, utterance 2, and so on. And then we have this last utterance. And at this point, the system is supposed to identify some relevant response. And in this setting, the setting is corresponding to some selection of the candidate response. So suppose that we have a set of candidate responses and only one is relevant, and this is the ground truth. So the goal is to select this one to provide it to the user. So that's the goal of selection. So we will have a mixture of correct response together with a set of irrelevant response, incorrect response. So that's the setting of a problem. So in here, the R3 is the desired response, which is both related to the context and also related to the document. Here, the colored elements are those that are mentioned in the document. Okay, so you can see that, those elements here are mentioned here. And the R1 is not related strongly to the last utterance, because in the last utterance, the question is it a long movie? So it asks whether what's the length of a movie, but the first answer is not about the length of the movie, although there is a long shots mentioned in the response. It's not about the long movie. So it is not relevant to the last utterance. Okay. And also R2 is not really relevant, although it mentions some facts mentioned in the document as these green parts. So here, what we want to say that R2 is something which is not strongly related to the last utterance, although it's related, is grounded in the document. And also another factor that we have to consider here is that this fact in green has already been mentioned in some previous term. So it is not necessary to just repeat the same information. So at the end, what we want to select is R3 in this example. And how we do that, and the key element that we propose here is to build a selection network, which we call the content selection network, trying to select a part of the document content to be incorporated in the selection of a response. Okay? And here, I can give a little bit of detail about that very quickly. So we have a document which will be selected by this selection network. And the selection network will use the context to try to match different sentences. And then there is a selection here. That is, only some of the sentences will be selected. An alternative way is to select the tokens, select the words instead of selecting sentences. So here we also select different words by using the mapping, and then there is a hard selection to build some representation of the set of words that we select from the document. So this is the selection process. And once this is done, then we will use the selected content to match with the response. And of course, the content, the context of dialogue will be used to match the response. So we'll have those two paths of matching, and at the end, we will have some global score for the response. I will not go into much detail about those formulas, which are quite standard. So we have the basic encoding of sentences, and then we have the document sentence selection or the document token selection, as I said. So basically we have a matching and then aggregation step. And finally, we have a filtering and the scoring. And what's different from the previous work is that we impose some threshold gamma to select the sentences or select the tokens. If the similarity or some this function is not stronger than the threshold gamma, then the sentence or the token will not be selected. So this is indeed a filtering step, and then we will produce some new score for different sentences or tokens. And also the second element that I mentioned is the decaying factor. That is, depending on the position of the utterance, we will determine how important this utterance or this sentence is, depending on what is the corresponding utterance in the context. A more recent utterance will assign a more higher importance to the corresponding sentences or tokens. So that's the key idea. And then we have different matching process that I'm not going into detail. So basically we have the context and the response matching, the document and the response matching, and we follow the two paths. And at the end, we will get a global matching score. Okay. Now, what I'm going to present is the experimental results, where the method I present here is compared with a set of previous approach, where typically we do some soft weighting, not really the selection. That is, we keep everything by using some attention weight. So that's the key idea. And what we can see that the performance of the methods we propose, with the method we propose here, basically is better than a soft selection. And we measure in terms of recall at 1, recall at 2, recall at 5, to see whether among the 5, 2, or first response in the ranking list, whether we have the right response or not. And we test that in two collections. One is a personal chat, where we consider the personal profile as a document. So the personal profile is a description about the person. That is used as a document, as a grounding document. And the second data set is about the movie. So we discuss different things about the movie, and that's used as a grounding document. So in both cases, we observe that the approach proposed is better. And also I have to mention that the among the candidates, we will have the correct candidate together with 19 wrong candidates. So the goal is to rank the correct candidates as high as possible. Okay, so that's the global experimental results. What will be interesting to see is to look at the effect of document content selection and the dialogue history decaying. The first figure tells you whether the document selection is useful. So here we have different selection threshold. If I put the threshold 0, That means I don't have a selection. I will use some traditional methods. It's just to weigh the different elements in the document. And if the threshold is 1, that means basically no content from the document will be used. So this is a non-document grounded dialogue. And in both cases, we observe that we have some drops compared to the best performance, where we do some selection, we do some hard selection. Okay, so this is the first observation. And the second one is about the decaying factor, whether we don't use decay or we use a very sharp decay. Sharp decaying means that we only use the last utterance without the previous utterances. And in both cases, we observe that we have decreased the performance compared to some decaying factor. And the best decaying factor we tested is 0.9. So those figures show the effect of the two elements that we incorporate into this approach. And another work that I want to present very quickly is about the knowledge-grounded dialogue. Well, the previous work is document-grounded, but here, when we talk about the knowledge, we may have different forms of knowledge stored in our system. That could be a graph, knowledge graph, or a set of triples. So you have a set of triples, which are just presented as a set, right? So you have still a dialogue context, and you can do some encoding and then decoding. And here, the decoding will be based on some selected knowledge. So there is a fusion process of the knowledge together with the information encoded in the system to produce an answer. So this is the generation-based dialogue based on knowledge. And if you go, I just mentioned a few existing work trying to generate responses based on knowledge. And one is still trying to encode the knowledge into some memory network. So you will use your context to read the memory, and some knowledge will be fetched out that will be used in combination with your context encoding to build your response. And the second approach that I mentioned here is to try to select the pieces of knowledge that happen to contain the right entity. Because if you observe your context, you will mention some entities. For example, in this example, we will have the entity of a movie name and also the director. So you just focus on the triples that contain those entities. So this is one way to select the pieces of knowledge from knowledge base. Here I would like to mention again some problem that we want to address in our next work. The way to incorporate knowledge, there are a lot of ways, for example, using gating so that you can select to generate some token from your model or from the knowledge base. There could be a lot of such approaches, but what we focus on is again on the selection to determine what pieces of knowledge are relevant to your context. And again, in the previous work, it is a kind of a soft selection based on attention. And here, the problem is that we don't have strong signals to know whether our knowledge pieces have been selected correctly. And this is because very often this knowledge selection step is one of the components in an end-to-end training process. And we don't have explicit signals to tell the selection of the knowledge, whether the knowledge is correctly selected. So this is a difficulty that we have with the previous work. So what we propose in the next work is to incorporate some explicit selection module to train a model to learn to select the right knowledge to be used in the conversation. So that's the work that I'm going to present very quickly. So the context is again about the discussion around movies. So we have the movies which are presented, described as a knowledge graph here. So you have the movie name, the actor who played in the movie, and so on. So this is presented as a knowledge graph. And also in this specific work, we also want to do proactive dialogue. That is, the agent tries to reach some goals. So for example, the goals here is defined as a set of entities that we want to cover during our discussion, during our dialogue. So this could have some recommendation purpose. For example, in our discussion, I want to drive the discussion toward some direction, and the direction is determined by those entities. So this is one simple method to define the goal, and this is defined in the data set that we use. So here is one segment of the dialogue which has been collected first by human users, and then we want to simulate the same process, the same response generated by the agent. Okay. So we have, as I said, we have a simple definition of the goal, and we have the knowledge base, knowledge graph that we want to rely on to move slowly from one turn to another, because it is not natural to jump directly to cover this entity. So we have to find some natural path to drive the current discussion topic to the topic about this entity, and then to the next entity. So that's the purpose of this proactive dialogue. Here I show you some segment where we try to, the bot tries to generate responses to cover the goal. So we have two entities in the goal. So we may start with some general conversation, and then the bot will lead to this first goal by mentioning the first entity in that response. And then later on, in a later turn, the second goal is reached here. So that will complete the whole process of a goal-oriented dialogue. So that's the system that we want to construct. So what we want to use here in this work is, again, some explicit model of for knowledge selection. As I said in the previous work, knowledge selection is only one component in the whole system. So we don't have any way to explicitly train this module by using supervision signals. So here we want to create some training signal to train this module explicitly. And also we have to deal with the goal tracking problem. That is, once we have a set of goals, and some goals may have already been achieved in the previous turn. So we don't have to go back to that goal. So there will be some unachieved goal that we want to achieve in the next round. So we need to track the goal in the dialogue. Okay. And the other things I will not go into detail because that's common. So what we have in that architecture is basically we'll have some basic encoding about the context, about knowledge, and about the goal. And then we want to determine what the goal has been achieved and what the goal has not been achieved. That will determine what will be the next goal or goals to achieve. And using those goals to be achieved, we can select the knowledge, the relevant knowledge that will lead us to those goals. And this is the knowledge selection module. And we will use some explicit supervision signals to train this module. And then once this is the knowledge is selected, we will have some representation of those pieces of knowledge that will be combined with the context, with the response in the usual way as I presented before. So here we will use 3 losses combined to supervise this second step. Now, some details, what I'm going to focus on is this explicit, well, first, I have to talk about the goal tracking. That is, we have some goal and the context matching to determine what part of the goal has been matched, has been satisfied. This is by a matrix M. And then we can say, well, some part of the goal has been satisfied to this degree. And what's missing is the complement of this satisfaction vector. And we will construct a vector to represent the remaining goal here. And that will be used to guide our selection of knowledge. In the selection of knowledge, we will first compare the context to goal to try to select what are the similarity of different pieces of knowledge with the goal and with the context. And then there is a selection here, the probability to select this piece of knowledge based on all the signals that we created before. But we also have some prediction loss that we will use to supervise the training process. That is, we want to build a model here. And the training signals is knowledge labeling. That is, Ki will be labeled as 1 if we observe that the object are triple, if the object of Ki is used in the goal response. And in that case, we can say, well, this piece of knowledge has been used by the human to generate the goal response. So this piece of knowledge, Ki, should be labeled as 1. So this is the piece of knowledge that we want to select. Otherwise, the piece of knowledge will be labeled as 0. And we use these signals to train a knowledge prediction or knowledge selection module. So this is something that we put in this work. And then we have the usual response selection process, trying to produce different scores. And finally, we have this score that will mix up the 3 scores, the score between the response and the context, between the response and the knowledge, and the response and the remaining goal. Okay, so that's the final process. And what I'm going to present here is, again, some experiments about the 2 data sets. In the first data set, that's a discussion about the movie, as I showed you. So we want to achieve some goal. We have the dialogue about movies. But in the second one, it also created by people in Baidu. So the first one is DoConv, and the second one is DoRec dial. So that means dialogue-based recommendation. So the goal is to recommend the different food, movies, and whatever by using dialogues. And we also want to mention those food or movies in the dialogue. So the agent will be guided by those goals. And what we compare here is the proposed model KPN with the do retrieval, which is a retrieval-based method, but using relatively simple methods, simple approaches. So it is based on BERT. And also the goal in that approach is just used as additional knowledge. It is not used as a goal, but used as a piece of knowledge. And it is just mixed up with the knowledge somehow. And also the selection of the pieces of knowledge is done by attention, so it is implicit. And in the same way, the other baselines that I mentioned here, the MEMNet is the memory network, and the post-KS is another method trying to estimate the the probability after using knowledge and before using the knowledge, trying to minimize the difference between them. And also another one, NKD, that use another approach, but all those approaches only use knowledge weighting. So there is no hard selection, not a hard selection, explicit selection of the knowledge. So we can see that using the explicit selection, we can do better. And also some comparison here is very interesting. So we have this complete model, but if we remove the knowledge, we can observe some drop, the drop in hits at 1, at 3, and the mean reciprocal rank. And we can observe that there is a sharp drop when we don't use knowledge. So in this case, knowledge is really essential. If we don't use the goal, that is, we just remove the goal, we have some small drop, not as much as removing the knowledge. And also, if we use the goal as a piece of knowledge, we observe, in fact, that it is not as good as not using the goal at all. So if we compare those two columns, the last column is even worse than without a goal. Okay? This is just to say that using the goal as a piece of knowledge is really a bad idea. Okay? So that's what we can observe. Now, let me check the time. So I'm running out of time. Let me just do a summary of the last work that I want to present. So it is about the grounding the answer in the question answering system. In the question answering system, what the open domain question answering system, what we usually do is to retrieve some documents based on the question. So those documents or passages are considered as a candidate. And then we will pass those candidates to a machine reader. And the machine reader will go through the document in detail, try to determine what's the start of the answer, where is the end of the answer. And in that way, we will determine the answer. We will extract the answer from the different passages. And at the end, we will have a global weighting of the different answers, and it will provide the first answer to the user. So that's the typical schema of open domain QA, trying to find an answer from a large set of text. But very often, as I mentioned here, the retriever, the first step, and the reader in the second step are disconnected. That is, the retriever typically just use an information retrieval method, for example, the BM25 model, to just identify the passages that contain the keywords in the question. And we don't care about whether that passage may contain some answer or not, because the answer is not part of the question. We don't have that knowledge beforehand. So we only use the question words to retrieve the passages. And we may retrieve some passages that contain the question terms, but not the answer. And this kind of passage will not be useful for machine reading. Let me illustrate the problem with that. The problem is that we may have different passages that the retrieval system may retrieve. So for example, the question here is, who is the inventor of helicopter? And we have different qualifications of this inventor. So he is a Russian immigrant to US, and he is the one who invented the helicopter. And the right answer is eagle. But when we check the different passages, candidate passages, in the first passage, we may have relevant elements such as the inventing or related keyword airplane, not helicopter, but it's related, and American and so on. So this first one could be retrieved by the information retrieval system in the first step. But of course, this is not the right answer because we are talking about other things. And in the second piece, we have a lot of related keywords. We have Russian immigrant. We also have the right answer, but we don't have the piece of information that we can use to support the answer. That is, we have some, he is the pioneer to in both the helicopter and the fixed wing aircraft. But we don't know whether Igor here is the inventor of a helicopter. So this is the missing piece. But certainly, if we just use IR, this will be this passage will be highly ranked. But it is not the right passage. And we have the third passage, P3, which mentioned the right answer, but not in the same context, not talking about helicopter or aviation. So it should be removed. And the fourth one is the right one, where we mention that this person invented or developed the first helicopter. And this provides some support to the answer. And this is the piece, this is the passage that we want to retrieve. But typically, you will observe that the P2 will be ranked higher than P4 and so on from the traditional information retrieval process. So what we want to do in this work is try to re-rank the passages to try to rank P4 before P2. And by considering not only whether the passage is relevant to the question, but also try to collect some signals to determine whether the passage may contain some answer. Okay. If there is some signal that tells you, well, there could be some answer in the passage for the question, then you will confirm that P4 should be ranked before P2. So that's the key idea. Now, so the work that we are doing here is to create a ranker between the two previous steps, trying to combine the relevance and the possible answer in the passage. And how we can do that? I will just jump to the solution that we propose. The solution is to use adversarial training, trying to tell a generator who would basically do the ranking by telling the ranker that we will have some relevance signal, whether the passage is relevant, and also another discriminator who will tell the generator whether the passage contains some answer, the right answer. So we will have two supervisions by those two discriminators to constrain the training of generator. So this is framed in the GAN generative adversarial training network, trying to train the generator under the constraint of the two discriminators. So that's the key idea. And I will not go into detail about the different formulas, and you can find in the literature that's the typical formulation. And at the end, once we have the first candidate selected by BM25, a traditional information retrieval engine, then we use our ranker, and then we use the reader. The reader is a typical BERT-based ranking, BERT-based reader as this one, which tries to determine the start, the end position, and the tokens within the start and the end will be proposed as the answer. Okay. So some results very quickly, and the results are on those data sets, which are the data set for open domain question answering. So we compare with only BM25, and we just use BM25 to rank the passages, or we use an existing system, QSDA, DSQA, sorry, that tries to rank the passages in a different way using the supervision of the noisy signals that just tell whether the passage contains the answer or not. So that's the only signals used in DSQA. So we can observe that using the GAN based ranking model, we can rank much better those candidates. And this is for the first collection, second collection, and we have similar results. Now, about the final answer, that is, once we apply the reader to select the answer, how accurate is the selection of the final answer? So we'll have different options using BM25 and then directly applying the reader, or using DSQA and applying a reader, or DR, dense passage retrieval, which is a recent model integrating the passage retrieval and the reading. And we can see that in those cases, when we compare with the existing work, the approach that we propose here with the additional ranker performs better. And this just shows whether the ranker is useful in those tasks. And here is the result of about the example that I showed earlier. So we have DPR ranking, and we can see that the P2 is ranked before P4, and in null ranker, P4 is ranked correctly before P2. And the number is just the ranking score. So the absolute number is not important, but the relative ranking of those scores is the most important. So this is the example showing that we can succeed in dealing with this example. And the final result is about the efficiency. Efficiency means that whether the ranker can rank the good passage on top. And we, as you can see here, once we use the number of passages to the reader to select the answer, you can see that once we have about 20 passages, it's the same as 50 passages. This means that we don't have to submit a large number of passages to the reader to obtain very good results. So the increase with the top ranked passages here is very large compared to other systems. This one is DSQA with a different ranker, and this one is something that does not use a ranking. So it is only the BM25 ranking, and then we use a reader to get the results. Okay, so that's the final observation. And in terms of time efficiency, the ranker is also efficient because it is at the end, we don't have a very complex network to use. So the ranking process does not take a long time. So that's it. I'm out of time. I will just wrap up quickly. So I hope that I have convinced you that grounded dialogue is important, because when you have a dialogue system, you don't necessarily always want to do chit-chat. You talk about whatever in the chit-chat without relying on some valid information or knowledge. So you want the dialogue to be grounded in a lot of cases. And the key questions that I mentioned in my talk is how to select the relevant pieces of knowledge or the pieces of document content to be used. And also, of course, we have to design some way to incorporate those selected pieces into the generation and selection process. And also, in the last piece of work, I talk about the question answering. So how can we select some answer from a document? And also, I wanted the document to support the answer. So it is an answer grounded in the document. And that will be important, because when you ask a question, you don't want the answer to be generated randomly. You want the answer to be supported by something. So that's the key idea. And well, I have not covered a lot of other things. For example, the grounding could be grounding on some emotion. And we can also incorporate the pre-trained model, as I mentioned, and I have not talked about that. And there are different ways, potential different ways to model the knowledge. For example, we can have the Jian-Yun to model knowledge graph. We may also want to combine symbolic reasoning with neural approaches, and there are some work on that currently. But finally, the last question is how we can evaluate the responses generated by the system. That's a key question that I haven't addressed in this talk. That's all, and thank you very much.
Yeah, thank you very much, Professor Neil, for your talk. So it is very informative and a very exciting progress. And now it is open for questions. If you have any question, please feel free to unmute yourself and ask, speak out, or you can type in your question in the chat area. I can read it on behalf of you and let Professor Neil to answer the question. Yeah, please.
Hi everyone, I'm Sajjad. Thank you so much for organizing this event, and also thank you so much for the very informative discussion talk. So the question that they have, so it's very obvious for me after your talk that the grounded dialogue is actually could be more important or even could be more useful than chit-chat, because as you mentioned, you try to support the discussion or the talk that the system provides with the participant based on some knowledge base or library or whatever you call it, some database probably. But the question they have, I assume that you gather some document or some knowledge, or probably some other people do this for you, and you use those database to support your system. But the question that I have is that, is it some assumption that you make that the topic is already available in the database? Because in some certain discussions, as you know, for example, even in our searches over the net, over the internet, probably I can search some topics that are not available on internet. And so it would be some, some corner case. So I'm wondering, how do you deal with those cases, or don't you deal with those cases in this specific project?
Yeah. Very good question. And indeed, what I assumed in my talk is indeed that in my database, in my document collection, there will be some relevant documents where I can find the answer. So this is specifically the case that I assumed in the last piece of work about the question answering. So the purpose, well, the first step is to select some relevant pieces of text, and then I read the text. What will happen if among the selected text, I don't find the answer? And that will happen. So in that case, what I should do, what the system should do, is to also have the response telling you that I don't have the response. And this problem has been addressed in some collections, for example, in the SQUAT data set, typically for machine reading comprehension, where you are provided with one text, and you try to answer some question. And in some cases, the answer is not in the text. So you need to say, I don't have the answer from that text. And this is typically the case for SQUAT 2. There are two versions of SQUAT. SQUAT is data set created by Stanford trying to test the machine reading comprehension. So in the first version, SQUAT 1.0, basically the majority of the question will find the answer in the text, but then they say this is not realistic, and they incorporated more questions for which the text does not provide an answer. So the importance of predicting that there is no answer is more important in the second version. Yes, so this is a very important problem, but I have not addressed this. Okay, and a very basic, well, typically one common approach that that is used in dealing with the SQUAT 2 data set is to have, well, typically data set will contains 4 different options, the answer 1, 2, 3, 4, and which is the correct one. And they add the 5th one by saying that I don't have an answer. So that's the way to incorporate that additional option into the selections.
Okay, thank you so much. Just another quick question. So I totally understand that this is a research project, and as you described, you probably deal with some data sets or database to develop your system. But I assume that one day you try this in real world application, and so probably your system will have some sort of access to external resources like internet. I'm just wondering for that case, again, probably it's not relevant to this talk, but in that case, uh, is there any approach to assure that the information that the system retrieve is, is true, it's valid, or because probably there are lots of, false information on the internet or external resources?
Yeah, that's another very interesting question. And indeed, that's very important because we can find a lot of information from the internet, from the web, but how can I make sure that this information is true? And I have not addressed that. And this is, for the moment, it is addressed in an independent or some other domain. People try to address the problem about the trustworthiness of information, how I can trust that information. And that's in a different domain. So people talk about the ethics or misinformation and so on. But here I assume that all the information that I have in my database is true information.
Okay, thank you so much, Professor.
Thank you. Any further questions? Yeah, I have one question. So when you do this grounding, how can we, first of all, do we assume that the knowledge base or the documents are consistent in terms that they don't contain any conflicting facts or conflicting information? And the second thing is that during the conversation to ground those concepts or pieces of information, how can we make sure the agent does not conflict itself during the whole conversation process?
Those are also very good questions. About the coherence of the knowledge graph, that's, for the moment, that's not the focus in the current research on dialogue. This is because we are still trying to deal with the coherent knowledge graph rather than dealing with the conflict that may appear, because this is certainly some realistic situation where you have a conflict, but this is still out of reach in the current research state. So people just don't deal with that problem. But I guess once we progress at some point, that problem will become important. So we started to address this problem maybe sometime in the future. But now I'm not aware of any work in dialogue or in question answering trying to address this problem. But this is certainly a very important problem. I know that this is a very important problem in the domain of data mining as well. So that's true. Okay. And the second problem is also about the conflict during the dialogue. And indeed, if you look at some examples by Xiao-Eis, the utterances may be conflict, maybe in contradiction. For example, a typical example is somebody asked Xiao-Eis what's the age, what's his age, and he said she's 20, and later on she asked, she tells another number, so it is inconsistent with the previous utterances. So that's a key problem, and this problem is being addressed by some studies. So people try to generate a response by checking whether my response will be consistent with what I already said before. Typically you have some personal profile, and once you want to generate something, you want to make sure that the response is consistent with the personal profile. also with the previous context. So there are some work in this area. Yes, I have not addressed that in my talk here.
Thank you. Any further questions? Yeah, again, if you have any question, feel free to just unmute yourself and speak out. Okay. If no further question, given the time, because it's already quite late at Montreal, yeah, let's thank Professor Lei again. Thank you so much for the very informative and exciting talk. And we look forward to further development, and maybe in the future, near future, invite you again to give us some further interpretation on the further developments. Yeah. Thank you. So
thank you very much for the invitation, and that's a very good exchanges that I want. Well, if we can keep in the future. Yeah. Thank you very much.
Thank you for attending. Yeah. Thank you. Have a nice day.
Thank you.
Thank you.
Thank you.
Bye.
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 Bye.